Hi and welcome to ChemSat, SAT Level Chem Explained. Just like in my other video, we will be discussing phase change, but this time we're going to take that concept and start to do some problems with it. In order to do these problems, we'll have to remember our formula Q equals ms delta T and what each of those letters and symbols mean. As a review, Q stands for enthalpy change. And M stands for the mass of the substance in grams. S stands for the specific heat of the substance. And delta T is, remember that T final minus T initial, which is the temperature change over a given period of time. Now let's take a closer look at S. We know that that stands for specific heat. And that's the number of joules of energy needed to heat up 1 gram of the substance by 1 degree Celsius. And the way that we write the unit for specific heat is joule per gram degree Celsius. As you can see, we've put joule in the numerator and 1 gram and 1 degree Celsius in the denominator, which makes sense because it measures how many joules for every gram and degree Celsius. This is also helpful when we're using our Q equals ms delta T formula, since we have our mass in grams, our specific heat in joules per gram degree Celsius, and then our delta T in just degrees Celsius. What does this mean for our equation? Well, because grams cancel out and degrees Celsius cancel out, Q will always be equal to some number of joules. Now we can apply what we've learned to solve a problem. The first thing you'll notice when you're faced with a problem is that they will provide you with a set of data that you may or may not need throughout the problem. So let's take a look at the problem. Let's say you have a glass filled with water, and we'll say that that water is at room temperature, so at 25 degrees Celsius. Then you add some ice to that water, and we'll say that that ice is at negative 15 degrees Celsius and weighs about 50 grams. And you're adding that to 400 milliliters of water. What we want to find out is the final temperature of the water after we add the ice. First, we're going to make a simple graph with an x and y axis. The x-axis will be labeled time and the y-axis will be temperature. Now we're going to start plotting some of the data. So we have negative 15 degrees Celsius for the ice. That will go around here on the graph. Our next data point is the freezing point of water, 0 degrees Celsius. We'll put that around here on the graph. And lastly, we have the 25 degrees from the water, which will go right up here. And now we're ready to graph. So when you add ice to the water, the temperature is going to go up. Now once it hits 0, it's going to start taking in energy, just like the helicopter, but in the form of heat. So there, it's going to plateau for a while and stay at 0 until all of it has melted. After that, the temperature is going to rise again, but we don't know how far since the T final is what we're trying to find. Simultaneously, the water is going to cool down from 25 degrees Celsius to meet the ice at that T final. So how are we going to solve this? Well, once again, the easiest way is to break things down and make calculations for each of the sections on the graph. So we'll go ahead and label the first one Q1, Q2, Q3, and Q4. Since these 3 sections collectively slant upwards, we can call that Q gained. And since Q4 is slanting downwards, we'll call that Q lost. So now we can start with our calculations for the first section, which is Q gained, and within that we can calculate Q1. And here we're just going to use our standard ms delta T formula. We will start with plugging in the 50 grams for the 50 grams of ice. Then we look over here and the specific heat of ice is 2.03 joules per gram degree Celsius. So we'll go ahead and plug that in. We don't need to put units just because we know that everything's going to cancel out to give us joules anyways. So now we'll look at the delta T, T final minus T initial. And in this particular section, the T final is 0. So we'll go ahead and put that in. And we'll subtract negative 15 from that. And that'll just come out to positive 15. And when we plug that into our calculator, we get that Q1 is equal to 1,523 joules. Now we're going to do our calculations for Q2. But unfortunately, we can't use ms delta T since our Ti and Tf are both 0, and that would just multiply to give us 0. Instead, we're going to look at our data and use our heat of fusion of ice, which is the number of kilojoules required to melt 1 mole of ice. But we're not given moles, we're given 50 grams of ice. So we're going to use some basic dimensional analysis. So we're going to take that 50 grams and we're going to multiply that by the molar mass, which is 18 grams per mole. And then the next factor is going to have 1 mole in the denominator, so they cancel. And we're going to look at our data and see that 6 kilojoules are required to melt 1 mole. Now we don't want kilojoules because all of the other Q's are going to give us joules. So we're going to multiply that by a factor of 1,000 joules per 1 kilojoule. So when we multiply that all out, we get that Q2 is equal to 16,667 joules. And now we're ready to move on to Q3. Since it's a slanting portion, we can use ms delta T again. And once again, we have the mass being 50 grams. But since it's water, since it's above 0, we have to use the specific heat of liquid water, which is 4.18 joules per gram degree Celsius. Now the delta T, that's the T final, we don't know yet, so we'll just write in TF, and 0 is the initial temperature, so that'll just come out to T final. When we multiply that all out, we get 209 times the quantity TF joules. Now we can move on to Q lost, which essentially consists of Q4, and that will be our last ms delta T calculation. So we'll start with 400 milliliters of water, and since water has a density of 1 gram per 1 milliliter, we can assume that 400 milliliters is equal to 400 grams. It's a 1-to-1 ratio. So we can go ahead and plug in 400 grams as the mass. If we remember, our specific heat is 4.18 joules per gram degree Celsius. Our T final is unknown, but our T initial we have, and that's 25 degrees Celsius. So we'll go ahead and multiply the first 2 factors and then distribute that to the TF and the 25, and we're going to end up with 1,672 quantity TF minus 41,800. In our last step, we're going to combine all 4 sections to produce the final answer. In order to do this, we're going to have to think back to the idea that Q lost is equal to negative Q gained. So our Q lost can be found right here. So we'll go ahead and plug that in. And that's equal to negative Q gained. So we're just going to add these 3 sections together. Q1, up there we can find Q2. And lastly, we have the 209 times the quantity TF. So from here on, it's all basic algebra. So we'll distribute the negative sign and add these 2 together. So now we have 1,672 times the quantity TF minus 41,800 is equal to negative 18,190 minus 209 times the quantity TF. Then we're going to move the TFs to the left and the remaining numbers to the right, and we're left with 1,881 TF being equal to 23,610. We'll divide each side by the TF coefficient, and then we're left with the final temperature being 12.55 degrees Celsius. And this makes sense since it's between our two initial temperatures. We'll go ahead and write that in, and congratulations, you've solved your first phase change problem.